Good morning, and welcome to part two of a discussion on bivariate regression and bivariate correlation. In the previous piece of this discussion, we had estimated that the slope, given the data examining the relationship between occupational prestige and age, was 4.94, and that the slope of x was negative 0.27. We had determined that 49.4 is the score we would expect, the occupational prestige score, where the predicted values line given by the equation of y bar equals a plus b times x sub I passes the y-axis at 49.4 units, or 49.4 is the score of occupational prestige, where that line goes through the y-axis. Now, saying that it's the score that we would expect when x equals 0 doesn't fit in this case, because our independent variable is age and it doesn't fit that we would expect an occupational prestige score for somebody who has 0 as their value for age. We have determined that for every 1 unit increase in a person's age, their predicted occupational prestige score goes down by negative 0.27 units, which was in contrast to what I had started out with, believing that we would see a positive association between age and occupational prestige. We determined that the coefficient of correlation was actually negative 0.30, which tells us, again, three things. First of all, that there is a relationship between a person's age and their occupational prestige score. The coefficient of correlation is not 0. It's a negative association. As the person's age goes up, the predicted value for their occupational prestige score goes down. And it tells us that there's a moderate association based on the idea that any observed correlation between 0.30 and 0.69 is classified as a moderate association. The final piece of information from the part of this that we did last time, we determined that the coefficient of determination, r squared, is 0.09. And that score tells us that when a person's age is known, we can account for or explain 9% of the variation in occupational prestige scores. So there is an association. According to our classification system, it's a moderate association. But the vast majority of the variation in a person's occupational prestige score, 91% of that is unaccounted for by a person's age. So what I'd like to do today is I'd like to run us through the second piece of this problem, and that is whether or not the observed correlation of negative 0.30 is strong enough that we would expect that it would likely exist in the population, and whether or not we could rule out random chance as the cause in the sample. So as we've done in weeks past, we're going to use a 5-step model to test our hypothesis. This week, the type of test that we're using is a test of significance for the coefficient of correlation. There are 5 assumptions associated with the test, more than any other test we've taken on this semester. But a lot of these things are things that we've talked about before. We've assumed random sampling, inferential statistics. This is kind of the common assumption. We're taking sample data and we're using that to make estimates or predictions about what we believe is likely in the population. Because it's a test that has 2 pieces, 2 variables, we assume bivariate ratio measurement, that each of the variables have interval ratio measurement. We assume bivariate normal distribution, that the scores on the independent are normally distributed in the population, that the scores on the dependent variable are normally distributed, and that the co-occurrence, the x and y co-occurrences in the population are also normally distributed. We're assuming that there's a linear relationship between the independent and the dependent variable. We've already confirmed that. Our coefficient of correlation score was not 0, so we know for sure that there is a linear relationship in the sample data. The fourth assumption is an assumption that's unique to regression and correlation, and it's the assumption of homoscedasticity. And this is the idea that the prediction errors are normally distributed in the population. The final assumption is that the sampling distribution is normal, and that's something that, again, is a theoretical concept. The idea that if we took repeated random samples from the population and we repeatedly used the data to calculate slopes, to calculate intercepts, to calculate coefficient of correlation scores, that those scores would be normally distributed, and that over time, if we did enough of those, we would actually get the parameters in the population. The average of those would be equal by definition of the central limit theorem and the law of large numbers to the parameters in the population. In the second step, we state out the hypotheses. Again, like the other tests that we've conducted so far this semester, these are inferential tests. So the null hypothesis is that there is no association between the variables in the population. The researcher hypothesis, in contrast, is that there's some association. Now, stated like this, we're implying that it's a two-tailed test, that we're not saying that there's a positive or a negative association, but just disagreeing with the null claim of no association in the population. We have a small sample test. The number of cases in our distribution is 15. We know that we had a distribution of 15 scores on the independent variable and a distribution of 15 scores on the dependent variable. Our sample size is still 15. But what happens is because we have two distributions of scores, one of those scores in each distribution is fixed by the sum. So we lose a degree of freedom in each of those distributions. So our degrees of freedom are actually n minus 2, 15 cases minus 2, 13 degrees of freedom. For a two-tailed test where the level of confidence in the test is 0.05, the t-critical score is 2.179. So our critical value, our critical region begins at plus or minus 2.179. And in step 4, we're going to use a very simple formula that we're going to compare to this t-critical score. Our t-critical score again, 2.179. I'm going to erase this piece of the board so that we can script out step 4 and step 5 of our 5-step model. Step 4 is our test statistic. And as we discussed, it's a t obtained score because our critical region is a t critical score. The reason it's t and not z is that the sample size is less than 100 cases. And according to our formula, we're going to take the observed coefficient of correlation score r, and we're going to multiply that by the square root of n minus 2 divided by 1 minus r squared. N minus 2 minus 1 minus r squared. The degrees of freedom minus the coefficient of determination minus 1, divide that, or take the square root of that, and then we're going to multiply that against the observed correlation of negative 0.30. So in converting the symbolic formula to a numeric equation, we simply substitute. We know that our observed coefficient of correlation score is negative 0.30. We're going to multiply that. There were 15 cases. Minus 2, the degrees of freedom we already know is 13. In the denominator, 1 minus r squared, which was 0.09. Bring down our negative 0.30. 15 minus 2 gives us a numerator estimate of 13. 1 minus 0.09 gives us a difference of 0.91. Bring this over here, 0.30. Under the square root, if we take 13 and we divide that by 0.91, we get an estimate of 14.29, rounded to the second whole number after the decimal place. So negative 0.30 divided by the square root of 14.29. I'm going to bring back our coefficient of correlation score. negative 0.30. I'm going to put a parenthesis around it to remind me to multiply. The square root of 14.29 is 3.78. So we've simplified the formula down to the final step where we simply take the coefficient of correlation score minus 0.30 and we multiply that against 3.78, which we got by taking the square root of n minus 2 divided by 1 minus r squared. So negative 0.30 times 3.78 gives us a negative t obtained score of 1.13. Right, so based on the data, the t obtained score is negative 1.13. The t critical score, where the degrees of freedom are 13 and the level of confidence in the test is a 95% confidence test, is 2.179. So in step 5, our decision-making phase, based on a comparison of the obtained score in step 4 and the critical value score in step 3, the decision in step 5 is fail to reject. And what we're failing to reject, again, is the no claim of no association in the population. All right? I'm going to come back to that. It's very important that we recognize that the tests in these tests of significance are always a test of the no claim, and that the no claim isn't about the observed relationships. We know what those are in the data. They're about what we would expect to see in the population. And at a 95% confidence estimate, we would expect to see 95 times out of 100, whatever played out in the sample, to also be the case in the population. At the 99% level, we would expect that 99 times out of 100. So we've successfully made it through the 5-step model for testing the hypothesis. We stated out the 5 assumptions, the 6 assumptions actually. We stated the null and researcher hypothesis. In step 4, we got the t obtained score of 2.179. In step 5, the t critical score negative 1.13, which yielded us the decision about the no claim of no association in the population, that we failed to reject the no claim. We see an observed relationship between the variables. The coefficient of correlation score was negative 0.30, but with 95% confidence in the decision and 13 degrees of freedom, we can't conclude with confidence that that relationship is likely to exist in the population. Now, the statistical power issue is that if we had 100 cases, 120 cases, the likelihood of rejecting the no claim perhaps would be much greater. All right, so in the end, we've conducted the work associated with the 5-step model, and we're tasked with the issue of providing an interpretation of the results. And as we've done in the past, there are 5 elements to our interpretation. First of all, we need to list out what the researcher interest associated with the test is, the type of test that was conducted to evaluate that interest. We need to restate the decision to reject or fail to reject the no claim, how confident we are in that decision, and what that allows us to say about the likelihood of random chance. So integrating those 5 components into the test that we just conducted, the summary would appear as follows. The researcher is interested in whether or not there's an association between age and occupational prestige. To evaluate that interest, a test of significance for the coefficient of correlation was conducted. Based on the results of the test, the decision is fail to reject the no claim of no association in the population. With 95% confidence in the decision, the observed association between the variables was not strong enough to rule out random chance. All right, we got all 5 pieces of those of the essential components of the write-up into the interpretation. The big thing to remember is that unlike the previous tests, for example, the 2-sample comparisons of means test, where we were evaluating the difference between distributions of scores, this is a test of association. It's about the strength. Okay? In this instance, the observed association was not large enough to rule out random chance. If our decision was reject the no claim, we would state that the observed correlation or the observed association was too strong to be due to random chance. Not strong enough, fail to reject. Too strong, reject the no claim to be due to random chance. So a very useful statistic. As I said before, it's my belief that these are the most useful sets of statistics, the ones that you're likely to see used time in and time again, particularly in the higher order statistics that some of you will choose to take on because you've had such a good time in this course. So this is the end of the lecture component for the semester. I congratulate you for making it through the course, and I hope you've had a good experience, and I wish you the best in your future endeavors.